Is my dear friend Luana Pedrosa from the Institute of Physics from the University of São Paulo. Luana.
Thank you. So thank you, Gustavo, for the introduction. Good morning, everybody. And so today I'm going to talk about this electrified water-metal interface, but actually I'm going to talk in general about water-metal interface. So inspired by Mariana yesterday, that she talked a little bit about herself, I'm going to talk a little bit by myself and why actually we are here today. So I started my undergrad in Brasilia, at the University of Brasilia. Fazio is not here, but I was going to say that was the best undergrad course he did there as well, but now Ilum is the best one, he would say. But by the time, there wasn't Ilum, so that was the best one to do. And then I moved to São Paulo, to the Physics Institute. That's where I met Mariana. So we are sisters, actually. We had the same advisor for the master. And then I went to Stony Brook University in New York for a postdoc. Then I did a second postdoc as the ICT Cipher in São Paulo as well. Then I got a permanent position at the University of ABC in São Paulo, in the metropolitan area of São Paulo. Then when I was there, I got this grant, this young research project of FAPESP, and was together with the Max Planck Society. And so I was this group leader, Max Tandem group leader. And then we had this money for the Max Planck, and then we planned, Mariana and I, we organized it, actually. We had even people already registered for this conference. We were gonna do a school, actually, on DFT and beyond, was the FHAM's school, and everything was organized. But then came pandemics, and we had to postpone it, and then we postponed it, and then came what was the name of another wave of the pandemics? So we postponed it again, and then we postponed it again, and then we gave up. So we didn't do the conference at the end, but then we had the money so now we did this conference. So that's why actually we're here. So for the German people especially, you should be thankful to the pandemics here because of that. So otherwise we wouldn't do that. So that's why you're here today. Anyway, so I had this project, and then I moved back to the University of São Paulo, where I am right now, with Gustavo. Gustavo is my boss there right now. So that's my brief history, where I am and why we are here today. So, okay, so then I'm gonna talk about my group. There is these atomistic simulations of electrochemistry. These are the group members right now. So we are in this building here. So I don't know if people are going back to São Paulo, but if you go, this is a very nice place to be in São Paulo, to do research, not to be in São Paulo in general. So this is the Physics Institute at the University of São Paulo, where I am right now. So why I'm gonna talk about water-solid interface in general, and not only the electrified. So water-solid interface, you can see this in many different areas, and then you can have different applications. So we studied some water semiconductor interface. This is important for photocatalysis, for solar cells. We also studied water gypsum interface, that it's important for construction, for using when you break a bond or things like that. So this was an interesting work, and we also studied a lot of water-metal interactions interface. So especially in this water-metal interface, if you think about even like long time ago, this voltaic pile, when we started doing this electrochemistry process, what you have mostly is some metal, some solid, and then some electrolyte here that it's mostly composed by water and ions on it. So we want to see what is the best system that you have to have, like, for example, a pile to have electrochemistry process. So before, people would just do like try and error. They would change the material and see which one was the best one. But we don't want to do that anymore. What we want to do is to study what is going on here in the system. So we want to use the quantum mechanics. So Mariana explained it a lot yesterday about that. I'm not going to go to this again. But the idea is that we want to see what is going on, why is the best material, why we should change, so which material we should use, using quantum mechanics, and actually using a lot of computational simulation. So we want to do high-performance computing for these systems, and then we can understand, and then we can design new materials, and then we can move on and then see what's going on. So that's the main goals of my research group, what I have been doing in the last few years. So the idea that we want to develop and apply methodologies for atomistic simulations of electrochemical process, including electronic effects and also nuclear effects, as Mariana pointed out yesterday and the other talks, that this is very important, especially when you have water, so I'm going to show some results about that. So what we want to do mostly is to, in this interface, we want to study the temperature effects. We don't want to do only zero. We want to see what happens when you include temperature. You want to do materials design, so we want to develop new materials. We want to study larger systems. Mostly important also, we want to apply an external potential to the system. And then we want to study, as I said, the quantum and effects for electrons and for nuclei. And more recently, what we want to do also is to do all of these, but for more realistic systems. So we want to use machine learning techniques so we can go to bigger systems and for longer time simulations. So that's what I'm going to show today, is what we are doing in the sense here of this, including temperatures, including potential, and all of this. Okay, so we start with this, with the temperature. So we have studied this for a long time. So we know that to include temperature is important because we wanted to study this electrochemical process in the temperature that we want to do the experiments. So we can do that quite easily using the ab initio molecular dynamics. Again, we heard a lot yesterday about that. So I'm not going to go in details again. So we did this study. By the time, this was a very long simulation because it was very computationally expensive to do that. So we studied this water-metal interface. And then we analyzed things like how is the water ordered at the interface. So we see that, so this is the comparison of two different functionals, so PBE and van der Waals. And what we are looking here is the average of the positions of the water only at the interface. And then we're seeing that when you use it PBE, we have these hexagons. So we have very ordered water at the interface. When you include the van der Waals, we still have these hexagons, but it's blurred here because they were like moving way more because they're included in this van der Waals dispersion. So we know that the including temperature was important. We analyzed the difference between the functions, but what we knew that including external potential was very important for those systems. We didn't want only to see for the neutral one, but we wanted to see the charged one. What happens to the interface, to the water at the interface when you charge the metal? So there were some experimental results showing that the water at the interface would behave differently, would basically flip when you charge the metal, so positively or negative, the behavior would be different. So we wanted to compare that. There was also a newer, more recently work, also experimental, where they showed that the interface properties depends on the potential that you are applying. And this was done for gold and WACOs and water interface. So we said, okay, what we want to study is a metal, some water here in the middle, and some metal, but we want to apply a bias here. We want to apply an external potential to this system. And then we realized that this system was very similar to people from the electronic transport calculation were doing by the time, where they used this non-equilibrium Green's function theory to study those systems, right? So what they have there was this left electrode, this right electrode, some scattering region here in the middle. They usually would put some molecules here, and they developed this. So this was the SMIGO code developed by Alexandre, and they were using these systems actually to see what was the current in the system when you apply some potential. We didn't want to see the current because we have a very large gap, but we have a very similar system. If you compare what you have here, it's a left electrode, a right electrode, and some scattering region here in the middle. So we said, okay, we can use those this methodology to study the system. So basically what we do is now that we apply this non-equilibrium Green's function, so we have this sigma, that is self-energy for the left here, the right half here, and now we have this the difference in the chemical potential, so we know exactly what is the bias that we are applying. We can define very well what is the potential that we apply. So we don't have the problem of adding a charge that you don't know exactly where is the charge is. We don't have the problem of being a periodic system. Now this is an open system. And then we can define very well what is the potential that you apply. So we did that. So we changed a little bit the code. We changed some things. So now we can use that for our system. The first prototype system that we studied was just one water molecule. So we did with zero bias, with negative bias, with positive bias, and then we see what was the structure of just one water molecule at the surface when you apply the bias, okay? So it's important to see when we say that we have a positive bias, actually what we have is that this interface is going to be negatively charged, and then you have this ramp of the potential. So this chemical potential is shifted up, and this one is shifted down, okay? So we did that, and then we have all the first results. So now we can use, so actually we did a lot of work in developing the code, and now actually we are using the Transiasta code, because it's way faster. This was a very expensive calculation by the time. And so now we studied this one molecule, and also we did with water monolayer, and we compared two different metals. So we did for gold, and we did for palladium. And why we chose those two different metals? Because they interact very differently with the water. So the gold one is more electrostatic, the interaction with when you have the palladium water molecule, you have more strong interaction between the water and the metal. So we did that, and then what we did was, again, we started with the minimum configuration. So we put the water there, and then we see what is the minimum configuration, and we have the water is going to be flat, which means that the dipole is parallel to the metal. And then we apply different bias potential, negatively and positively, and see what happens to the water molecule. So for each potential here, we just relax the system and see what happens. And then we see this is for the gold. So it started with this 2.82. This is the distance between the oxygen and the metal. And then we see what happens to the distance and to the angle. So this is the angle. I don't have the figure here, but I have in the next slide anyway, but it's the angle we are seeing with the normal to the surface. So basically what we want to see if the water is going to tilt or not, how it's going to rotate to the interface. So we see that for gold, we don't need a very large bias, that the water molecule already rotates and flips down when you have a positive bias, and then when you apply a negative bias, it goes to the other way and goes up. And then you can see one important thing here is that it's not very symmetric, so you need less positive bias that the water molecules already rotates down. When you have a negative one, you need more to go up. This is because of the interaction between the oxygens and the metal. So we did the same for, okay, so this was to show how it rotates anyway. So we did the same for palladium, and then you see that for palladium, you need way larger potential for the water molecule to rotate it. And again, this is because of the way the water molecule interacts with the palladium. As I said, it is a very stronger than in the case of gold. So if you compare both of them, you can see this is palladium and this is gold. So gold, it goes down faster than it goes faster in the sense of the bias, not in the time, but what is the number of or what is the potential that you need to apply compared to the palladium one. You need way more here, than here for gold. Okay, so now we have the structure for one single water molecule. What we analyze also was how is the vibrational frequencies, how it does change when you apply the biases. Again, we heard yesterday that this vibrational analysis is very important because they can probe it experimentally, so we can see if the water molecule is binding, how is it binding to the metal. So we did that. So this dashed lines, it was the original when you have just the water metal without bias. And this is the bending modes and the stretching modes. And then you can see, so this is the zero bias. And then you can see that especially the stretching modes, they change a lot when you apply a bias. And of course, this is related because you are changing the position of the water molecule to the metal. So we compare this again to the gold and then to the palladium. And then we see that for palladium, this changes way more than for gold. And again, because of the stronger interaction between the water and the metal. So this is what we did, and I said, okay, now we can go beyond, and then we can put a larger system. So now we are analyzing an ice here between the gold. So we did like analysis with what we call 1H ice, that is have a proton disordered system where the net dipole of the system is 0. We also did analysis for the ferroelectric 11 ice, where you have a dipole, a net dipole here. And then we wanted to see, basically what we want to study here was this property of that the water, when it is confined, the dielectric constant of the water changes a lot. So when you have the bulk water, the optical constant dielectric is 80. When you confine this system, they were seeing this experimentally, that the constant goes up to 1.82. So it changes a lot when you confine the water. So we wanted to see if we can study things like that. So because now we have pretty much a capacitor here. So we have the metal, we have the metal here, we have a dielectric system here, and then we apply the bias so we can calculate the capacitance. So we started only with the gold. So we wanted to see what was the capacitance only for the gold. And then now we apply the bias, we can see what is the charge in the system, and then we can calculate the capacitance, right? So we did that only for the gold. And then we can calculate the capacitance. We have the delta rho. The delta rho here is what is the difference when you have zero bias, when you apply a bias. So you pretty much have the V, and then you have the charge, and then you calculate the capacitance. But now the problem is when you confine those systems, we start having some issues that is how you can define the distance between the plates. So we know that we can calculate the capacitance like this, but we also, in principle, for a macroscopic system, you can calculate the capacitance using the geometric properties of the system. But now we started having issues on how can you define this D, the distance between the planes. For a macroscopic system, this is very well defined. You just see what is the distance. But when you do this for a very small system, in the nanometer regime, then it started having issues. So we can calculate first in using the distance between the atoms here, that's these lines here, and then we see that they have an error for the capacitance compared when you calculate it using just the charge. And then, okay, it's a very small error, but we didn't want to have that, but when you include the dielectric, this becomes an issue. So we see that we can actually calculate this capacitance not using the distance between the atoms here, but integrating between the position of the charge, where exactly it is the charge. So when we do that, we recover the capacitance for the gold capacitor very well. So now we develop all this methodology, I would say, to calculate the capacitance based on the distance, not the interatomic plate distance, but using the charge, as we can see what is the peaks of the charge, and then we use that for a dielectric system now. We include the ice, and then now we can recover what the experimentalists were seeing, that you have a very small constant, dielectric constant when you confine those systems. So this is a work that we have just submitted, and then we are analyzing all the systems. Okay, so anyway, so that's the electrified water metal interface that I wanted to show, but we also want to study more realistic system, as I said in the beginning. So we don't want to do only one single water molecule. My goal, to be honest, would be to study an electrolyte, not only water, but put some ions, include nuclear quantum effects for the water molecules at the interface. So we wanted to see larger system. We went to the dynamics for a longer time. So to do that, we know, and we heard a lot yesterday, that one possibility to do that is to use neural networks, to use machine learning techniques so we can increase our systems. So just for the students actually to have an order of magnitude of what we are talking about, when we have just 64 water molecules, if we just do an ab initio molecular dynamics, this is a little updated, but of course, but the order of magnitude is the same, but it would take for you 1 year to simulate 1 nanosecond simulation doing an ab initio molecular dynamics. But when you use those neural networks methodology now, you can go up to 1,728 molecules, and then you run just in 8 hours. So I always joke with the students that now they can do mistakes, because in 8 hours, then you can fix what you're doing, and then you can go and do another simulation. If you do a mistake after 1 year, then you lose your fellowship, so no, there is no way. So now you can try and error, things like that. So it's a way better thing to do. So that's what we want to do. We want to do simulations with the same quality as DFT in these simulations here, but we want to do faster and then for larger systems. So that's what we developed. So we did this work a few years ago, where we actually, one thing that was very important here was how we sample the configurations that we are using to train for the machine learning, for the neural network. So we spent a lot of time here. We heard something about that yesterday as well. So what we did here, we did a classical simulation with using a classical potential, but we did with different temperatures and different densities for the water. And we selected those configurations based on this function here, that actually what we are doing is we look at what was the radial distribution function of the water for those simulations here, and we selected configurations that were maximizing these radial distribution functions. So we are sure that we have small values for the OH distance and larger values for the OH distance. So we are pretty much like having a sample of all the possible configurations that you have for the water molecule. So we selected 18,000 configuration. That's a lot. We actually had another paper where we showed that we can decrease this number. We don't need those much configurations, but we did that in the first work. But then with these 18,000 configurations, what we do is that we now do the ab initio calculations to get the energy and the forces for those configurations, and then we did that for 4 different functionals. PBE and 2 using van der Waals, and 1 that was the MetaGGA, that is the scan. And then we now train our system using those 4 different potentials. We have 4 different neural networks, and then we use that to do the molecular dynamics for those for the water molecule, but now using a larger system, longer time, and we included nuclear quantum effect, as Mariana showed yesterday, that is important for water. So the first thing that we did, of course, is just to see the G of R, and one thing that it's important to say here is that the system size doesn't change that much the G of R for water. Even if we increase the system size and if we do for longer time, PB is always very bad, and it's not a matter of system size. So it's very structured, the water here, as you can see, though the dashed line is the experimental one, and then you see that the PB is always very bad, and it doesn't matter what is the system size. One thing that was important that we analyzed was the self-diffusion coefficient for those systems, and we did as a function of time. Now we can go to very longer time. And then you see that it takes a while for the system to converge the self-diffusion coefficient. So there was some results, previous results showing that the scan has a good self-diffusion coefficient, but actually this was a matter of time. When you keep going with the simulation, you see that it goes back to a not very good result. And then we can actually see the final results here for the self-diffusion coefficient. And again, we see that no matter how long you simulate and the system size, the self-diffusion coefficient is very bad for all those functionals. This is the experimental result. This is what we have. PB is always the worst one. Pretty much the water is like an ice here. It doesn't diffuse very well. So we said, okay, what we can do is to improve this and then include nuclear quantum effects. Again, Mariana talked about that yesterday. So we used the path integral molecular dynamics techniques here to include these effects. And then we can observe difference, of course, in the OH, not that much for the oxygen, but the structure change when you include here for the nuclear quantum effects when you have the hydrogen, that is the light atom. But what we actually see that it's more important is for the self-diffusion coefficient. So again, so this now we have less time, because it's still expensive to do. So we have only 300 picoseconds for this simulation. But again, you see that takes at least 100 picoseconds to converge the self-diffusion coefficient. And this is something that we wouldn't be able to do without this neural network. These simulations with nuclear quantum effects are very expensive. So this, what I'm showing here, that it takes a while to converge. But now you see that the results are way better. So Gustavo yesterday was asking, is this really important, the nuclear quantum effects? And yes, it is, especially, of course, for water. So again, PB, it's always bad. Doesn't matter what you try to do, it doesn't help. But for the other functionals, you see that now at least we are in the same order of magnitude of the experimental value. So of course, it's not perfect. None of this functional is perfect for water, but at least now you have some improvement for the self-diffusion coefficient. So this was something that was important to show, and this we wouldn't be able to do before without the neural network. So including nuclear quantum effects, it's very important for water. We saw this yesterday, and I just want to emphasize again that we wouldn't be able to see that. Okay, so we have this for the liquid water. So what we did now was, okay, now we can try to study the ice system. So we started with the ice 1H, that is the proton disordered system. It's the same view, just so they form these hexagons, but they have this net dipole that is 0 in the system. And what we did is we used the same neural network that we had before for the liquid water, and we just added some few configurations for ice. An important point to say here is that that's why I emphasized how we chose the configurations for the liquid water. In principle, we have a very good neural network for water. We said we don't need to add some ice configurations, so we did first some results for the ice only with this neural network here. The results are quite good, but we said, okay, let's see what happens when you include some configurations of ice. It changed a little bit, but not that much. The qualitatively results are very similar, but anyway, the results I'm gonna show is for a neural network that we added some configurations for ice. So we did the same protocol, we did for the same functionals here, the analysis, and then we did only for the nuclear quantum effects. And then I show first the structure of the radial distribution function for the ice. And then this is the oxygen. And here, it doesn't change that much when you include the nuclear quantum effects. So the dashed dotted line are the experimental one. This is the nuclear quantum effects, and the solid line is without nuclear quantum effects. So for the oxygen, it doesn't change that much, of course, because the light atom is the hydrogen, but you can see there is a little bit of the shift of the position of the peak here. It's a little bit hard to see, but you can see that it's always a difference in the peak of the oxygen, of the first maximum of the oxygen distance here. And this is gonna be something that is gonna be important. So there is a small shift. But when you include the hydrogen, so now you are seeing for the oxygen, and hydrogen radial distribution function. The effect of the nuclear quantum effects, of course, is important. So again, the dashed line is when you include the path integral, the nuclear quantum effects, sorry, and then the solid line is when you don't have. So you can see, for example, here, let's say this is the OPT B88. So was without nuclear quantum effect. This when you include, and the experimental results are here. So you decrease a lot the maximum of this first peak here. So what you are seeing here is that the distribution of the OH changes a lot, and then it gets softer. That's what you want to expect. And even for PBE, you increase a little bit, but again, of course, not all the functionals are very good. For water, we know that, but we know that when you include the nuclear effects, you get better results than you have without nuclear quantum effects. So including these effects was very important for the structure. You improve a lot the result, but not everything is so good. So the density is very bad for all these functions. So this is the density for the ice without nuclear quantum effects and including nuclear quantum effects compared to the experimental results. So you see that all of them actually increase a lot the density. So you don't reproduce well the density of ice. And then this is because, as I mentioned here before, that you have for the OA-OO distance, you have this shift here. What you're doing is that you're overbinding the water ice with those functionals. Even when you include the nuclear quantum effects, what you're doing is that this shift, you are making the hydrogen bond stronger than what it should be, so the density increases, and you don't have a very good results for the density for this 1H ice. We also analyzed the frequencies for those systems, the vibrational frequencies, and again, you can see a very difference between the system without nuclear quantum effects and with nuclear quantum effects, and here is the opposite, so the dashed line is with nuclear quantum effects, and the solid line is with nuclear quantum effects, and the dashed one is different. But again, you can see there is a very big difference between those, especially for the stretching modes here. And this is, again, this is important because these stretching frequencies here is going to be the probe to see how is the hydrogen bond, how they are interacting. So then you can see that it's a very strong difference between those systems. Okay, so this is something that we are doing with Mariana, and then we are finishing this work now. So as I also mentioned before, we wanted to do bigger systems, larger systems for more realistic systems. So now what we are doing is training these neural networks for water-metal interface. So we started doing, again, we started with our liquid water neural network, but we added some just gold configurations, and then we added different configurations for the water clusters and monolayers at the interface, and then it trained a neural network, and we did that. And we don't want to do a universal force field here. We saw that this is very actually hard to do for those systems. And then we trained it using these configurations here, and we saw that the results were really bad. So what we learned here is that actually you need to include a liquid water configuration on top of the metal. So you need this long-range interaction to properly see what's going on. So now we have a better neural network, and now what we are doing is systems like this size. So we have 10,000 atoms. We can simulate we have done first 50 picoseconds, but now we know how to do this neural network. We are also doing for the ice. We have a neural network now for ice-metal interface, and we can do these very large systems. So in conclusion, that's what I wanted to show, that I hope that I convinced you that we have now a methodology that we can apply the bias, that is an ab initio methodology. We can define very well what is the potential, and we can also include the temperature effects. We can do that with ab initio molecular dynamics, or we can include the machine learning techniques, and we do all of that together. And we can also include nuclear quantum effect, that it's very important for water. So now we have all the tools that we want to study different systems, and then we can go for more realistic systems, and then we can design more specific materials for electrochemical process, and then we can do a lot of work using all this methodology. So thank you for attention, thank you for the foundations.
Thank you, Luana. So the talk is now open for questions. Please introduce yourself as well.
Hi, my name is Robert Meissner. So I actually do the follow-up talk. I have one question to the capacitance. When you calculated it for the ice phase, I know that when you have water in confinement, the capacitance actually doesn't behave like a plate capacitor. Did you see or did you observe some deviations from this like plate capacitor law?
You mean considering like a capacitor in series or something like that, considering that layer, things like that?
Because the water is at the interface having a different structure, and that basically changed a little bit the
So
capacitance.
what we did here was only the electronic response. We are doing only for the optical, so we are not looking for the difference in the structure here. So that's why we studied ice and not water. So we have this configuration. We are also doing some studies with water, then becomes different because of the configuration here. But what we did in this work, actually, that was the motivation here before, was to see, because of this interaction of the water with the interface, now you defined the width, the distance, and also what is the charge, if the charge comes from the metal and from the water. So we have this, now we are doing this way of like integrating these when you see exactly what is the charge, and then we also do, what we do is that we remove the metal, we apply just an electric field in the ice and then see what is actually the charge, and then we separate the effects from the metal and from the ice itself. But we are only looking for the electronic response. We are not looking right now for the configuration.
Anderson from University of Delaware. So in the calculation for of the self-diffusion coefficient for water or ice, did you try removing one molecule so that you have a lower density effectively?
You mean here or for the... This is for the liquid water, right? So this is looking like just the average for all the water.
When you compare the density that you get with the experimental value.
This one? The ice density.
Right. So that density from the experiments, would that correspond to a given concentration of missing molecules? Did you?
We are not doing, for this one, we are not doing with defects right now. So I don't know if
but
it is.
a defect, a missing molecule, I'm not talking about removing an oxygen or hydrogen, but one molecule. Would that increase your coefficient of?
I think Mariana can actually no? No, so we are actually here right now, we are only looking like for, we're doing an NPT actually simulation, and I don't know exactly if it's gonna correspond when you remove one water molecule. This I don't know.
Yes, it's just the third question. I'm Mariana Rossi. I spoke yesterday. So I'm also, it's super cool, the capacitance work. In those experiments, they also see that the capacitance perpendicular or horizontally is very different, and it changes in different directions depending on the confinement. Here you can only calculate one component.
We're doing
right?
only for the perpendicular right now.
And do you think there's a way with this methodology to get the other one?
Yes, but what we wanted to do, that's actually my student somewhere here. We wanted to do like larger systems so we can have better confinements in the other direction. So right now we are only doing for this perpendicular direction. But if you have this model that we can increase, then we can look for the horizontal and the perpendicular. But yes, the methodology is general enough, and it's also general enough to do for water system and then see the difference for the configurations, as Albert was saying.
Yes. Hi, Christoph. I also spoke yesterday. I had a question about those ab initio simulations of the water interface at palladium and gold, especially about the dynamics. Do you know what would be the residence time of a water molecule in a given position, or some estimate of time scale of reorganization of the interfacial structure?
You mean this one?
Yes. And well, how does it compare between the two metals?
Yeah. So they're like the time that they arrange here is quite fast. So it's like 1 or 2 picoseconds. So this was very fast. Actually, what we saw, this was a very small system, to be honest. So the water here was very confined. So we had only 8 water molecules here. So we had pretty much 20 angstroms between those two plates. So we didn't recover the bulk water here. So this was a confined water. So what happens is that the interface is very fast. So if this was the question. And we did for gold as well. This it's not showing here, but I have the results in this paper for gold. Again, it was a very small system. And what we saw is actually, even for van der Waals, you also ordered in these hexagons. So you pretty much recover this. What happened here is that you don't see it very well. It's because on time it fluctuates, but you see the hexagons there. So it's still ordered, the interface. And this is for both palladium and for gold. But this was quite fast. We did some simulation as well using a polarizable force field for these. So we modeled a force field that was charged, was like a rod model where you can charge. And then you see the same patterns for the interface. So now we can have, we recover the bulk because we could do like very large system, but the interface is very similar to what we had this before.
Okay, any more questions? If not, let's thank Luana again. Thank you, Luana. And now we'll have Robert Meissner, is that it? From Hamburg University of Technology. And we'll continue discussing water.
Yes. Oh, the microphone. Sorry. Okay. So yeah, that will be a bit tricky to coordinate. As you can see, I already changed slightly the title. So before it was energy storage, and I realized upon doing this slides, it's more related to energy harvesting. A couple of words. So what I will show you today is a new project which got funded, which is quite prestigious in Germany. It's called BlueMat, and it's all about water-driven materials. And many of these slides I will show you are actually also from colleagues, experimental working colleagues, because I think that's a nice motivation and illustrates nicely what we plan to do. Yeah, as Mariana said, we met in Lausanne, and basically that was where, yeah, our research collaboration started, and I went to Hamburg. It was very nice to see that also Mariana moved to Hamburg a bit later, so we continued working together, and also Mariana is involved in this rather big project, which is nice. And yeah, to start a bit, I like to show this steam engine from James Watt. You probably all know this. It's rather old. It's also an AI generated image. So apparently there are no two suns, and I actually don't know if this machine really works. But yeah, James Watt used water as a macroscopic working fluid. And in the steam engine, and basically this steam engine was quite disruptive and triggered the first industrial revolution, and also enabled many new scientific fields like thermodynamics, hydrodynamics, etc. Yeah, and today, 50 years later, we want to use water not as a macroscale fluid, we want to use it as a nanoscopic fluid in these kind of blue materials. So the idea is we want to redefine the rule for creating new materials, and instead of making the materials rather complex, the electrolyte rather complex, we want to use a simple working fluid, which is water, and the material should derive their unique functionalities from this water. You could ask, why water? Because yeah, why water is quite abundant. It's basically, it covers 70% of the surface of our planet. It's the working fluid of the planet, so it drives the climate, it drives the weather, and it's also our cells' life's matrix. And it has exceptional properties on the macro scale. One is probably well known. It's the large surface tension, and you can basically always have some sort of drop. And this large surface tension also allows the Jesus bug to walk on the water, which is quite fascinating. On the same time, this large surface tension also has some implications on the capillarity, and you probably all know that the thinner the capillaries get, the higher the water rises, and in a way it defies gravity by that. And masters of this mechanism are actually trees. So these trees can grow up to quite high heights, like 100 meters, and they are able to pump water from the soil up to the leaves on this scale. And in a way, they are like these masters of pumping without a pump, actually, because they use nanoscale functionalities in their leaves, and the ability of pumping that water from the soil up to this 100 meters is actually defined by the pore size in the leaves. So that's quite fascinating. So if we can build very tiny pores, can we also build artificial trees? And in a way, this is correct, but there are some challenges. I will come back to that now. So on the nanoscale, you have like these tiny pores. You see here the capillarity. That's actually an image from simulation we do from last summer, actually. And this capillary will then rise, and water has this large capillarity, which is nice, but it has even more interesting properties like an exceptional electrical conductivity. So if you confine it into between two surfaces, you even make pure water quite electrical conductive. So there's a colleague, Vasily Artemov, who wants to actually create a supercapacitor by using not an electrolyte, by using pure water and confinement of the water. So that's quite, a fascinating approach. And you can tune the electrical polarization quite nicely of water. And there's another interesting aspect, which is we call it nanofluidic superconductivity. So for certain diameters of nano confinement in carbon nanotubes, for example, water basically has no friction on the walls. And so you can apply very low pressures to move water through that pore. So that would be quite interesting, and analogously to the electrical superconductivity, we thought of a term calling this nanofluidic superconductivity. So there's a lot of work from different colleagues, Laurent Joly and Ludovic Bouquet, of course, who are like pioneers in this field, and I gave a couple of them. There are many more to discover when you search for those names. So on one hand, we have disadvantages. On the other hand, we have also some challenges, which is the high mechanical stresses involved during such processes. And I had to look it up, and I find this word quite interesting. You are always involving yoctoliter fluids. So that is a very small amount of water. It's 10 to the power of minus 24 liters. So imagine if you want to filtrate something and you are involving yoctoliters, that process can take a while. So that's a little bit the issue. These we want to address more or less in this BlueMud project. And the colleagues at the TUHH, they are really good in producing nanoporous materials. And I brought them here. So this is, for example, a nanoporous metal. It can be controlled and made hierarchically porous on different length scales, from the nano up to the millimeter scale. This is a nanoporous silicon, which you can even 3D print then as a tree. You have some photonic materials. Those are typically oxides with quite interesting optical properties. And we have the aerogels, which are like somehow biology related. And if you now add water, you get the blue materials. And one nice example is nanoporous glass, Vicor glass. And what happens if you dip that into liquid water, the water will imbibe into this glass. And you see here an imbibition front, which shows a nice square root T law. It's Lucas-Washburn law. And also the width of this imbibition front tells you something of the nanoporosity of this material. And yeah, you can describe that quite well. And you can even use that to write with water. So that's also an idea we had in this project. And what you see here is this Vicor glass imbibed with water. You shoot an IR laser onto it and evaporate locally the water. So you can write with it. And after a while, this will vanish again. Okay, while the colleagues actually can do this materials, and we have nice facilities to do imaging. For example, here is the XFEL allocated in Schenefeld and the DESI in Hamburg. So this is a bit outside of Hamburg. And this is nanoporous silicon, and they do holographic imaging. Here's a water droplet, and now if you let the water droplet approach the surface, and here you have a snapshot time of 20 femtoseconds, you see that the water touches the surface, then imbibes into this nanoporous silicon, and you can nicely see this imbibition fronts progressing here. So we can do nice imaging, we can do nice materials, but we are still lacking somehow the molecular understanding and the molecular imaging of this, and there's where we can help, we theorists, and that is where I now start with some of my research, some of my recent research. So we took this nanoporous silicon. I grabbed a model from a friend in my time back in Bremen. So this is called MCM41. It's a nanoporous silica with a pore diameter of 3 nanometers and a wall thickness of 1 nanometer. It was 12 nanometers thick. And we basically added a little bit of water on both sides, and then we let the water flow using an NPT ensemble into the pore. And what happened was this: you basically, here's the start, then you form these capillarities. The capillarities will meet, and when they meet, the pore is full, right? This happens on this square root T law, which was quite cool. What we did additionally, we also let the walls flexible, so we don't fix them. And there are two interesting things happening here. You have some deformation of the pore then. You have a lateral deformation, which is more or less in this direction, compressing or an expansion of the pore wall thickness. And you have the axial one. And what I show here is the imbibition length, so how high the water is in the pore. This is the blue line, and the lateral strain. And you see that these pores laterally, they expand a little bit, and that is because of two effects. You have the Bangham effect, which releases surface stress because of the water releasing some stress due to the interaction with the surface walls. And you have the Laplace pressure, which is like contracting actually the system. And interestingly, when these two capillarities meet, you get a jump in strain. This is because the Laplace pressure is suddenly reduced, and then you get this stress. So that is lateral. Then you have axial. And axial, you actually only see the Bangham effect, mostly. You might speculate that there could be some Laplace pressure drop involved here, but yeah, we actually couldn't observe that, and this also scales a little bit with the stiffness of the material in that direction. Okay, now we have understood how water, relatively well, how water imbibes into nanoporous materials. And the idea is now to use such a system, not silica, in this case silicon, to harvest energies, electrical energy. And a colleague, Patrick Huber, actually thought of a very simple system where you use imbibition and drying to harvest electrical energy. And I will guide you through this process, and we start with this upper part. So what happens if you have this nanoporous material which really likes water? It will imbibe water. You will form some sort of double layer, will form some surface charge, and you have imbibition-induced currents, which you can use for electrical energy. Once this thing is full, you can reconnect the wiring, and you can use the sun to dry this specimen. And upon drying, you will have again a drying induced current, and you can harvest the electrical energy again. And they did, you can repeat that cycle back and forth, and they did some calculations that in contrast, comparison to solar cells, they don't perform too bad. And yeah, you actually don't need the sun to evaporate the liquid. You can also use waste heat, and there's a quite large amount of waste heat produced in these HPC computing centers, so around of the order of 100 megawatts in Germany. And the issue is it's like low temperature waste heat. And with this systems, you could try to at least regain some of the electrical energy here. There's another nice example, which was actually in the German television. So here you see the Elbphilharmonie, the tide, the River Elbe, which basically wets and the sun dries then the amorphous silicon, the nanoporous silicon here. And by the wetting and drying of the tides, you could also harvest energy. And a colleague asked me, hey, why you need the tides? And it's actually true. There could be a person just wetting the surface with a sprayer would be also enough. Yeah, so here another level of complexity was added. We have charges and we have a potential. And in order to understand this, we need to go away a little bit from silicon, and now we go to, we add another level of complexity in a way. And most of the times, this imbibition is hindered by the water friction, so the normal hydraulic resistance, which gives you this nice flow profile here with the slip on the walls. And the idea is now to cover the silicon with maybe graphene from the inside, and then you could achieve some fluidic superconductivity due to the size of the nanopores, and then the water will flow easily. And in addition to that, you could also allow the capillarities to change if you apply a potential, and that's a quite nice idea. With this approach, you could actually create some sort of reverse tree, which could be used to basically remove the humidity, the water from the air, and basically extract it in a way to for water harvesting. Yes, so that's blue mud, and there are certainly more ways to recover electrical energy. And one particular way, which I find quite interesting, is the thermoelectrolytic Seebeck effect. And now we start with constant potential simulations. And what you see here is two graphite electrodes, water with sodium chloride included, and one side is cold and the other is hot. So what people thought of, probably you all know the Seebeck effect. You bring two metals with a temperature gradient and you get a Seebeck potential. The same happens actually with electrolyte, because the ions diffuse differently in the water upon a gradient. And when you cool one side, heat the other side, people thought for a long time, oh, it's the ions which drives this thermoelectrolytic Seebeck effect. But this is actually not true, and we found out it's actually not the ions, it's the water at the interface which behaves differently. So you can do a simulation with a temperature gradient shown here, and you will see that you have some different structuring at both interfaces, which result in a total potential difference at the end. So this is basically the thermoelectrolytic Seebeck potential. You can run also isothermal simulation to check this result, and indeed the difference between the bulk potential here and here, between the hot and the cold simulation, is exactly what you observe here. So our hypothesis was then, okay, it's not the ions, it's something at the interface, and it's basically the dipole of the water which orientates more strongly if it's cold and less strongly if it's hot. And that basically explains you this potential difference. So what now seems quite obvious is to do a multipole expansion and really check, is it the dipoles, is it the quadrupoles, is it the monopoles which do this potential difference? And people do this. So here you can see the multipole expansion, you see the monopoles, the dipoles, the quadrupoles. You see it's depending on the Z position here only, you see the charges, and it appears that it also depends somehow on a reference. And this reference is problematic. Because if you want to locally decompose the contribution to the electrostatic potential, depending on this reference choice here, so we tried several, you change the dipole contribution to the total potential quite a bit. So it even changed the sign, right? And it becomes even worse, the quadrupole does the same. So that means this doesn't tell you anything. You can, by arbitrarily choosing your reference point, you can choose whatever you want. You can say, well, this contributes a lot, this doesn't contribute, or this contributes even negatively. So really bad. The only thing which works is actually when you integrate over it and this potential difference. And you see here, the dipole actually, at the end, is always the same for all of these reference positions, and the dipoles produce the potential difference, while the quadrupole doesn't contribute at all. And if you add both together, you also end up with your typical potential profile inside your cell. So that's good, but you see often in literature that people decompose that and then they try to explain something with it, and it's actually not true. So it doesn't tell you anything. There's a nice work from Ludwig, who studied this in greater detail and also explains how the shift can be analytically derived. So I recommend, if you're interested, to look into that. Okay, for all these kind of simulations, when applying a potential, you need some special software. And actually we develop such kind of software. It's called Electrode, and it's available in LAMPS. So when you download LAMPS, you have the Electrode package available. You just need to compile it. And you can different things with it. You can do constant charge, you can do finite field, you can do constant potential, you can do image charges approaches. And I show you now how this works for a very simple example. So it's gold and water with sodium chloride inside. And if you now apply a constant potential to the system, you can track the total dipole of the system. And you see, oh, it behaves somehow weirdly. It's not an exponential behavior. It's actually a bi-exponential behavior. So if you fit then a bi-exponential curve, one for the water dipole and one for the ion dipole, and this is nice in simulation because you can decompose that, you see you have different time scales. The water dipole actually initially drops down a lot and then slowly decreases again, while the ions act on another time scale and basically compensating this strong water dipole in the end. So you have these two time scales working, and often case this is completely ignored and people just focus on the ions. But like if you apply a potential, it's really the water ions which initially give you the dipole. Okay, you can do even more with this approach, with the electrode. You can do, so this is a 2D periodic system. We have also different Ewald solvers for 2D periodic systems. You can do even 1D periodicity, for example, carbon nanotubes. We have a thermopotentiostat. In this case, the potential and the charges can fluctuate. We have a Thomas Fermi model involved, so you can go also away from ideal metals and model real metals, which basically we have implemented, but we don't have developed this the theory behind, so I give it here. And what you can even do now, okay, sorry, it comes on the next slide. I want to go a little bit more into details of this electrode approach. So what we actually do is we have the total Coulombic energy, electrostatic energy. We collect here. This depends, of course, on the positions of the electrodes, which we keep fixed in this case, and the charges on all electrodes. We use Gaussians for the charges. And you can basically collect all electrode-electrode interactions in this A matrix. That's very important. You can also collect all electrode interactions in this B vector. So you have a matrix and a vector, and you have an applied potential, which is basically psi times Q, the charge of your electrode, as an additional term. So in the end, what happens, you want to minimize this. So you do the derivative of du by dq, and set it to 0. Then you end up with this expression, and you can say, well, okay, when I minimize the electrostatic energy, I can get some sort of optimized charges by doing a matrix inversion, bringing the A to that side, and you get your optimized charges. And this is exactly what electrode does. And we did it in a quite fast way by using the particle mesh solver in this case, which speeds it up like a couple of times, multiple times. And what you do is actually you bring your positions onto a mesh where you can basically do the Fourier transform, the fast Fourier transform, much faster and much more efficient. And then you project it back to the real space system. So that's what we actually do. We have described that in this paper here. And yeah, this is more or less now available. And what we added, because this is under continuous development, we added also conjugate gradient. And this might be interesting for many of you, because with the matrix inversion method, you are somehow restricted to fixed electrodes. Your atoms basically are at the same position, so you calculate A once and then you are done, which is often case not very useful if you want to check this inhibition dynamics, right? So you can use a conjugate gradient. It also saves a bit of memory because you don't have to store this A matrix, but it's on the other hand a little bit slower, 3 times roughly. But yeah, it's now implemented, and there's even some more addition right now. It's the charge equilibration method. So if you compare this equation with this equation, you see there is some similarity. And actually the only thing which is added in QEQ is this electronegativity here. And the rest you collect in the hardness. So J is more or less called an effective hardness. It includes all the A matrix terms and also the QEQ hardness parameters in a way. You set this to 0, then you solve this, and you basically get your QEQ charges. And there are, in this case, so previously, Rapé and Goddard basically introduced that approach. They used NS Slater type orbitals, and I can tell you they are a mess, and they are complex and computationally really not easy to handle. So we use Gaussians. And if you want to use Gaussians, you have to reparameterize a little bit the QEQ parameters. This is what's shown here for SI, OO, and even for the SIO combination. So red line is the Slater type orbitals. Blue line is the fit from fitting Coulombic energies to Coulombic energies of STOs. You see, you can fit them nicely. And also the combination of SIO with a combination rule. So here we didn't fit, matches quite well. So okay, we thought now we have a nice potential for running silicon dioxide simulations, and oh boy, we observed some differences. And that's, I think, the biggest problem with QEQ. There's a lot of different approaches. It's not really clearly explained what they actually do. And in this case, basically, what seems to happen, so these values for the density for different SiO2 polymorphs agree very well with experiments, and also with the paper, with the values mentioned in the paper of Demiralp and Rapé and Goddard. But what they did is, for QEQ, they used, in a way, charge distributions, and for the electrostatics, they again used somehow point charges, which is somehow like a little bit inconsistent. And when you use Gaussians in both cases, yeah, your densities are off. Also, you see some spurious 90 degrees SIO-SI angles, which are really bad. And actually, they didn't show these plots in their paper, and I know actually why. So this really screams for a reparameterization of SiO2, but yeah, it works. We also checked, because this is some issue with electrode and also with QEQ, you need to invert the matrix. If you are not able to invert the matrix, your algorithm will be unstable or even fail. And you can check if this matrix is invertible by calculating the eigenvalue, the minimum eigenvalue. And if this minimum eigenvalue is below 0, then you have a problem. You cannot invert the matrix. And calculating this is rather expensive, and you won't do this on the fly. But I can tell you in QEQ, if you use commonly hardness values, you are safe for any width of the Gaussian, more or less. So the higher the eta value, the smaller the Gaussians get. I don't know if you're aware of the EEM method, which basically is QEQ, but with point charges. So you could say, well, okay, if we make our Gaussians smaller and smaller, we arrive at Gauss, we arrive at point charges. Is our simulation still stable? And I have a colleague doing this for TIOX. And indeed, if you choose your Gaussians too broad, you get a lot of deviations of the charge, particularly at the surface. If you are now in this region here for the Gaussian width, you get a better agreement. And if you get even narrower with the Gaussians, the charge difference compared to EEM is rather slow. So also here, our algorithm works quite well. QEQ and EEM, you can do both with this approach. And for infinitely small Gaussians, our points converge to EEM. There's another thing which you can do with QEQ, which I find quite interesting. You can also model the quantum capacitance, which is quite important for graphene. And this is basically done by describing the charge density using Gaussians. So here you see the sum over Gaussians. Sigma basically tells you how wide is the Gaussian. And if you change the sigma, you basically can change the delocalization of the electrons in some way, to some extent. And in this paper, we could show that there is a nice relation of the sigma to the density of states at the Fermi level, plus an additional potential. And when you use this, so you can convert this equation back and forth to sigma or to the density of states. And you can basically, if you know the density of states at a certain level, you can define U as sigma. You can use that in the simulations then, and nicely you get the differential capacitance correctly for like aqueous sodium chloride between graphite. And experimentally, those are the dots, and you see there's a kink. And when you use this approach, scaling the width of the Gaussians, depending on the applied potential, you nicely reproduce that curve here with shown in red. If you don't use this, you basically get a flat line for the system, which is not physically correct. Okay, you can also look at the water again, and this is quite interesting. So here you see 0 volt and 1 volt, the electrodes, and nicely also here, it's not the ions which actually introduce the charge on the surface, is the water. If you look closely, the charges are not induced where the ions are, they're actually induced where the water reorients. And in this case, what happens is that the hydrogen bond network is broken, and the hydrogen then points downwards, inducing some positive charge. And you can check this also by calculating the free energy of accepting hydrogens or donating hydrogens for the oxygen. And you see for 1 volt, accepting 2 hydrogens actually is less favorable than having just 1. And that basically indicates that these hydrogens really tend to point to the surface, inducing the charge. Okay, so this is all classical MD, but we also use machine learned force field, of course, because for graphene it's nice, but for gold there is a problem. If you want to simulate gold with a classical force field, you typically get hollow side absorption of the water, and in reality it's on the top side. So this is impossible to solve with radial symmetric potentials, and you need probably to go to machine learned force field. We did that, so we had a rather large database of ab initio calculations where we basically calculated the flux of electrolyte under different stimuli, also on combination of different stimuli. Quite nice. So we used that data to train a machine learned force field, in this case a second generation high dimensionality neural network potential for different surfaces. Also committee learning we learned before was used, was quite successful. This here was a bit challenging because you have one element more. But in the end, this allowed rather big surfaces to be simulated, and you could reproduce, at least for platinum, this double peak which you observed in the contact layer quite well. So the blue water molecules, they are relatively fixed on the surface, which is this peak here, and the red ones are a bit more mobile. And also you can calculate a 2-dimensional radial distribution function, and you see that you get some anisotropic behavior depending on which direction you go of the structuring, which is also quite heterogeneous due to these dots. We also looked at the surface corrugation by calculating the potential energy surface, and you see what you expect: graphene, smooth; platinum, very rough, and that basically leads also to a correlation with the friction coefficient, like you would expect. The higher the corrugation, the higher the friction coefficient. You can also use these machine-learned force field now to calculate the hydrophobic transport, and that is a nice approach by Alessandra Serva, where you basically calculate the empty volume, the probability of forming an empty volume with some radius, and these are these colored curves. So those are the probability of finding a certain empty volume close to the surface for different radii. And you see, if you have a very small cavity, it will approach, this is the blue, it will approach the surface a bit closer. If it's larger, it will be further away, and also the whole fluctuations are a little bit shifted. And from that, you can also calculate the wetting. And this is quite nice because you get what you would expect. Graphene is roughly a little bit below 90 degrees. That is also in good agreement with a recently published paper by Roland Netz, who basically did a meta study on all published contact angles on graphene. And yeah, platinum, for example, then is basically completely wetted. You can also check how hydrated the surface are by calculating the dividing surface of water and the surface here. You can do some statistics. You get these tails, and you see that platinum and gold, they tend to be more strongly hydrated, while MOS and graphene less strongly, because of this tail being a little bit more away, telling you you have a higher probability of these instantaneous surface to be more separated. Okay, and because we discussed also many neural network potentials, and there's a huge zoo, we also experimented a little bit with a graph neural network. In this case, it's maze off, and we basically use it out of the box to reproduce our results. And what you see here, you can simulate rather big systems. We calculated the slip lengths with these two approaches, and they are in quite good agreement, like considering that it's like out of the box. You also see a nice agreement in this 2D RDFs. So it's homogeneous, it's isotropic. Also the density profile looks fine. Also here, these colored lines correspond to that lines here. The density also in this direction is nice. So it's quite amazing that maze-off works so well, and it's also rather cheap compared to the 2G HDNNP. One last slide, what is a little bit of an outlook. So here you see magnesium, and magnesium is also quite interesting for me because that's on the Hereon site in Hamburg, and you see magnesium corrodes a lot. So this is hydrogen created at the surface of magnesium. Here are little impurities, ppm, you form hydrogen bubbles, they dissolve, and yeah, the corrosion of magnesium is very strong. And imagine you have now a magnesium implant in your body, you don't want to have that bubbles forming inside you. So we have a lot of papers where we did machine learning for quantitative structure property prediction, how to add little organic molecules to prevent that. But my idea would be to use an all-atom approach to simulate that. So use these infrastructure we have available, couple this with LAMS and the QEQ approach we recently published to model such complex interfaces. So that would be quite some goal. And as a last remark, people in the past said, if you can do something with silicon, do it with silicon. And we want to change this mantra in BlueMat, and we want to say, if you can do something with water, do it with water. And with this, I thank you for the attention. I thank the group, particularly Ludwig and Ole, who basically created a lot of the work I showed here, and also Lars. And yeah, I'm open for questions.
Thank you, Robert, for the very nice talk. So the talk is open for questions now. James, you have a microphone.
Very nice talk. Thank you. So your potentials are reactive, the neural network ones, from what I saw of the corrosion. No?
In principle, they are. So we didn't check the corrosion. They are not reactive yet. They are just describing the surface layering. If you want to add reactivity, that would be on another level. That would be very complex. So
okay.
right now we didn't.
Anyway, can you still get like adsorption on surfaces of hydrogen, oxygen, OOH?
No.
No.
No, the water
Okay.
stays. The water doesn't split right now.
Okay.
So that would be the last slide, like with the magnesium, for example, because magnesium is very reactive. You can easily split water on magnesium.
No, not talking about splitting, just adsorbing like an OH on the surface.
But for absorbing an OH on the surface, you need to split the water.
Okay. Well, thank you.
More questions? So I have a question. So you have used MACE as a foundational model to make your, but nowadays people are discussing several different models, several different flavors. So can you comment a little bit on that? Why have you chosen that one? What are the perspectives of other ones and so on?
So but that's a good question. So this second generation neural network potential for MOS2 was actually super hard to train because instead of 3 elements, you had 4. And this made the training almost impossible. So we thought of, okay, these neural network potentials, they don't scale that well with the number of elements. MACE does a much better job there. And I think, that's for the future, I think it's very promising. There are, on the other hand, is kernel methods. And the more you add training to these kernel methods, as Mariana said, the more memory they will consume. So it's also limited. And I think the best compromise in that way are these graph neural networks.
Okay.
Yes.
Gabriel.
Thank you for the talk. And I have one question about the different behaviors of the 2 different temperatures electrodes.
Mm-hmm.
And the question is, actually is a curiosity, if this different time scale behavior could be accessed for experimental methods such as high frequencies impedance, electrochemical measurements, and it could be used for example, sensing different surface modifications, for example.
Mm-hmm. I think that's a good idea. There's the group from Mathieu Salan and Simone Pezzotti, I think it was Simone, who did the impedance calculation using a constant potential approach. So you can also get a reasonable impedance description from this nanoscale systems. And it's quite interesting to see that all the macroscopic models for the impedance work somehow also for the nanoscopic models. So we are also doing that kind of simulations right now. But I guess it's a nice idea to check if the functionality of the surface has an impact on impedance. Yeah.
Thank you.
Okay, so let's thank Robert again. Thank you, Robert. Now, James has some instructions, or?
Yeah, just a quick note. Please, if you plan or don't plan to go to the serious visit today at 5, go to the website and fill the form. We need to know how many people will go. So we need all of you to go to the website and then just say yes or no, okay? Yeah, next section is just Christian Carbonio. That's here, and then we'll have a very long lunch break. Thank you all. The next session will start, people. So let's start to move to the auditorium. Thank you. No, because we need for the online.
Okay. So in this session, we will have only one talk by Christian Carbonio from Fritz Haber Berlin, and he will talk about heat and charge transport in real materials. Thank you, Christian.
Now it's working too much. Good. Hello, everybody. So let me start. Actually, it's my first time in Brazil. It's my first time in South America at all. So I really enjoy it, and I want to start by thanking the organizers, especially Luana and Mariana, for inviting me, for giving me the opportunity to come here. I immediately feel at home, maybe because of my Italian roots, I don't know, but it's really enjoyable. So let's start with science. I mean, my talk is quite broad, and I'll try to give you some overview and some little glimpses into some insights that we gained over probably the last 10 years. So what is heat and charge transport at all? When I'm talking about that, I actually refer to a macroscopic picture. So you really have a big piece of bulk, you heat up one side, you cool the other, you have non-equilibrium, and you get a heat flux trying to re-establish thermodynamic equilibrium. And the actual particles that are involved in there that are transporting the energy are photons, electrons, and nuclei. And it's the exact same for charge transport. You actually have something like a voltage difference or voltage gradient, and then you have electrons, ion, and polons, so all particles that have a charge with them that will contribute to a charge flux trying to reestablish a charge equilibrium. And you can even have a coupling of these fluxes. We've seen that in the talk before by Robert, and this is the Seebeck-Competier effect, where heat flux induces a potential gradient, or vice versa, charge flux induces a temperature gradient. Now, this research area is very interesting from my point of view, because you have on the one side these practical applications, but you have a wide range of basically solid-state quasi-particles contributing. So you have to deal with basically all kind of areas of solid-state theory. And this is what makes it challenging and interesting. One common ground in this theory is that these actual processes are governed by the microscopic dynamics of the materials. So what is actually happening is that your nuclei are never static, they always move, and this induces some friction. And with that, that is the fundamental reason that you get macroscopic laws like Fourier's law that relates heat flux and temperature gradient, and Ohm's law that relates charge gradient and potential gradient and charge flux that work at a macroscopic scale. And this friction coefficients, so the electrical conductivity and the thermal conductivity, are determined by the microscopic dynamics. And this is exactly what I want to talk about in this talk, and give you a little bit an idea of what is happening, how we can calculate that, what are the ideas behind it. Now, let's start very simple. We ignore charges problem at first, and we even make the heat flux problem simpler. Now, photons are interesting, but they're actually only relevant in transparent, incandescent materials, when your material is really so hot that it's glowing. Then there are electrons. We'll get to them later when we're dealing with charge transport. In metals and degenerate semiconductors, they're very important also for the heat transport, but in insulators and semiconductors, we can ignore them. And so we're left with the dominant contributors in insulators and non-degenerate semiconductors that are essentially the phonons or the nuclei. Now, what are applications of this? Just two very quick examples. One thing, for instance, the semiconductor technology. Back when I started with my first PC, it has something like a transistor like that, or CPU like that, with 10 to the power 6 transistors. Nowadays, we're essentially 4 and 5 orders of magnitude more dense in transistors. This has led to an enormous miniaturization, and this leads to local hotspots at the nanoscale. And if you look at industry roadmaps for next generation GPUs, CPUs, one of the key challenges is getting the heat away of these local hotspots as efficiently as possible to increase longevity, to increase efficiency. Another side of the medal is actually turbine technology. This is where actually my interest in this all started back when I was at UCSB, actually neighboring Anderson's office. We were somehow office mates almost. And there we started with this zirconia ceramics. And they're applied on top of the superalloys of turbines because they're extremely insulated, and they're able to drop something like 100K over 100 microns. So half a millimeter of coating generates a temperature drop of 500K. This obviously protects the superalloy from the high temperatures generated during combustion, but more interestingly, this allows you to increase the combustion temperature. And each airplane you ride today is actually running at a temperature that is roughly 200, 300K higher than the melting temperature of the superalloy. And the only thing preventing the melting is this ceramic, this ultra-insulating ceramics. And again, industry roadmaps will tell you that next generation turbines need to at least get even higher temperature gradients active, and this is an important material science problem. So let's stop with applications for now. Let's really look what the physics behind that is. Now, if you go to standard solid-state theory, heat transport theory, and you want to describe how actually the dynamics in your solid looks like, you immediately end up with a harmonic approximation. So you model your potential energy surface by a parabola. This is a very efficient theory, because then you can decompose this problem. You get this kind of nice phonon band structure that are based on this harmonic theory. But the key idea that makes this computational method so efficient is that you have decoupled modes. And in turn, this means that each phonon is independent. It has an infinite lifetime. It does not see the other phonons in this harmonic theory. In turn, this leads to an infinite thermal conductivity, since these particles can propagate without friction. So to account for heat transport, you have to go beyond that. And you have to account for anharmonicity. One way to do that is, for instance, by perturbation theory. In the particle picture, this basically introduces scattering events. So your phonons can scatter from each other, and you can calculate the scattering cross-section, putting in your favorite transport theory, and then you can calculate thermal conductivities. This works nicely for a lot of well-behaved materials, but it's a low-temperature approximation. The basic idea is that harmonic models work, and all what anharmonicity does, it's a small perturbation on top of it. So essentially, it's also a close to equilibrium approximation. That is very useful in some systems, but we are actually interested in high-temperature refractory materials, in complex materials, where often you're exploring a large portion of the potential energy surface, including various minima, and so on. And there, you have a problem, because then you start getting strongly anharmonic effects that you cannot really describe by perturbation theory, and the actual anharmonic contribution become dominant in driving the dynamics. So how can we describe that? Now, so far, we've done essentially PowerPoint science. I've tried to sketch you, okay, this is probably a good harmonic system. This anharmonicity is a little bit stronger. Here we start getting problems, and here, when we have imaginary phonons, it's not even clear what is going on with the harmonic approximation. And one of the first goals we had is to basically go from this PowerPoint picture to a more fundamental material science kind of metric. So can we quantify anharmonicity in material space? And the idea is pretty simple. What we did, we just ran molecular dynamics and started to compare how good does the harmonic approximation really predict what we see in DFT. This, for instance, you see here for silicon at 300K, you see your DFT forces and the harmonic forces normalized to the same maximum value. You see this has a perfect, nice correlation. This is what I call a machine learning plot. They're very happy when they get such a result. And indeed, what this tells you is that you have a material that is very harmonic. The harmonic approximation works very nicely. On the other hand, here you have copper iodide at 300K, also zinc blende structure. It's nothing particularly uncommon. Here you see the broadness is already much higher, and you even have points here in which DFT and harmonic approximation point in a different direction. And as I will also argue a little bit later, what this implies is that you have a potential energy surface that looks like that. You have a second minima, and actually when you're sitting here, harmonic approximation and DFT point in different direction. That is the source of these large outliers. Now, in a more simple way, you then can look just at the broadness of this distribution, calculate the standard deviation, and introduce an anharmonicity metric. Do a little bit of algebra and maths, and what it turns out that is nothing else than a measure on how much the anharmonic effects contribute to the forces on average. So here we have something like 0.15, meaning 15% of the forces on average stem from anharmonic effects. Here we have 0.50, so 50% of the forces stem from anharmonic effects. Now, the question is, okay, here we have 50% anharmonicity. Can we treat that with perturbation theory? What are the implications if we try to calculate the thermal conductivity for that? And if you use standard perturbation theory in all its kind of fashions, see experiments gives you something like 1.7 watt per meter Kelvin. Perturbation theory basically overestimates that by 350%. Usually, not everybody is very used to this kind of units, what this implies. But just to give you an idea, 1 watt per meter Kelvin is the thermal conductivity of wood, so of an organic, completely disordered material. Single crystals have typically 2-digit thermal conductivity, something like 50, 60, 100, 180 watt per meter Kelvin. Diamond reaches 280. So here we have a single crystal, copper iodide, perfectly thing that exhibits a thermal conductivity that is comparable to an organic material. So where is this coming from? And to understand that, we obviously need a theory that goes beyond that to reproduce experiment to understand what is going on physically. Now, what we've undergone to do that, if we developed a method that is based on the Green-Kubo theorem that allows you to get the thermal conductivities from simulations of thermodynamic equilibrium. This goes back to the fluctuation dissipation theorem, and beside what you actually have to do is to calculate the autocorrelations of the heat flux. The nice thing is it works in thermal equilibrium and really accounts for all anharmonic effects. What's not so nice is that it takes you quite a lot of work to basically implement this thing, to find a definition of the heat flux and to converge it. It's not that simple, but over the years we were able to do that. Here I just give a glimpse. So what you actually do to define this heat flux, you need a continuity equation for the energy. You integrate that up by introducing an energy decomposition, essentially saying each nucleus has a certain energy, and then you get this relatively intuitive definition of the heat flux that tells you this is the time derivative of the energy barycenter. Now, a definition like that is very easy to achieve in something like a force field, where you easily know which nuclei are interacting how with each other. It's a little bit more tricky in DFT, where you get the total energy of the system, but not the energy of the individual atoms. So here we did a little trick. What you actually do, you take this time derivative and the sum, then you get two terms. One is velocity times energy. This is the so-called convective heat flux. This is the energy that is transported by molecules when they're flying here across the room, for instance. So they are important in liquids and gases, but they're relatively unimportant in solids where you have limited atomic diffusion. Then you're left with this virial term that essentially describes the work done by your motion against the field of all other atoms. This is unique. You don't have to introduce a partitioning. It's maps on phonon. It's well-defined for classical potential. It's well-defined in first principle frameworks. It's just a pain to implement. But then you can do it and you get something out. Just a side note, this thing gets even more ugly if you go to machine learning potentials, because there the energy is a function of many different atoms. So if you're trying to do that, I point you to the work from Marcel Langer that has really done an excellent work in going down this many-body route and finding formulas to evaluate this kind of heat flux efficiently, also machine learning potentials. No more numerical details. Let's skip to the result. Here we've done that, and you see actually it's quite interesting to get now really a result that is comparable to experiment. It's much closer than perturbation theory. This is satisfying, but the actually interesting question is why? What is happening at the atomistic level? And there you can then start mapping it back to a quasi-particle picture. And what I'm showing you here is basically phonon frequency versus inverse lifetime. So those up here have very short lifetimes. Then you can go back to the to the 60s, where people starting thinking about this problem, and you find a very nice kind of theorem, the Joffe-Regel limit, that tells you actually to define a quasi-particle, its lifetime should at least be longer than one oscillation period. If you start having lifetimes that are shorter than one oscillation period, you can hardly speak of an oscillation anymore. And this is what we're seeing here. Down here we have long enough lifetimes. This is where the phonon picture applies. But up here we have modes that have a very short lifetime that does not work anymore in the particle picture. And this is basically the many-body explanation why this material is so anharmonic. If you're more a real space guy like I am, it's even easier to understand. We looked at the dynamics, here the MD, and then we mapped this anharmonicity over time. What you see for a long time, it's oscillating around this 0.5 value, but sometimes you have these jumps. And if you analyze this kind in more detail, you see that in this blue region here, we indeed get a nice zinc blended structure of copper iodide as it should be. But here in this red area, we have the formation of Frankel defect. These are short-lived defects. They live for a couple of picoseconds, so this copper forms an interstitial, you have an oxygen vacancy, and this basically kills your heat flux. So again, we're coming back to this picture. This is exactly what I was talking about in the beginning. Here we're exploring different minimas of the potential energy surface. And let me just note, you don't even need to form this defect. It's enough that you're trying to do that all the time, that the system tries to explore this barrier all the time to really introduce this strong harmonicity. And this brings me already to my first take-home message. So capturing the strong anharmonic effects is crucial for describing thermal insulators. Now, we've not done that just for copper iodide, but actually for more than 100 materials. Here, 30 where you see have good experimental results. So these are somehow a validation slide, and you see we have something like a mean absolute percentage error of 25%. That is, I would claim, even lower than the experimental measurement errors if you go through literature. And even in this low regime, we have mean absolute energies of 1 watt per meter Kelvin. So this is very nice, but each of these data points is roughly 1.5 million CPU hours. That was all done a couple of years ago, where we had really to go through the whole ab initio route. So can we be faster? I've already told you we have now a heat flux for machine learning potentials. Can we get potentials that are good enough? So that we can do. And if we do that standardly and try to just run MD to basically explore the potential energy surface, what you will end up is basically sampling the first 5 picoseconds here. So we'll sample the first at the minima here, the equilibrium, and then if you fit your machine learning potential, you get something like that. So you will oversee the strongly anharmonic effect. Now people will tell you, yeah, you can easily solve that by using active learning. And thanks, Christoph, for introducing that yesterday. So you use some kind of uncertainty amount to do an active learning scheme and try to explore this kind of uncertain regions. In other words, what you introduce is an acquisition function that depends on the uncertainty. By definition, the uncertainty is large where you don't have data. So as soon as you leave this blue region, the uncertainty grows. Now, barrier here, and this will improve that. At the same time, however, you will also get points here in this high energy region because the uncertainty is also large here. On this 1D plot, this doesn't look too bad because you have one interesting point and one boring point, so half-half, it's a good deal. On real potential energy surfaces, you're dealing with 3n degrees of freedom, of which 1 is interesting and 3n minus 1 are boring. So this is it's a working, but it's a very inefficient scheme to describe barriers. So what we actually did there to get a better description is use energy-weighted active learning. So you use this kind of uncertainty, but additionally put on some weighting function, something like a Boltzmann that kills off this high energy kind of values, and then you are really exploring the lower energy regime. This is a much more efficient scheme to get these things right. Just an example, going back to copper iodide, what you see when applying this, if you start with just no active learning, 0 iteration, you see that indeed you don't see this kind of minima here. You're overseeing it, as explained. And then you put in this active learning scheme, you see that it increasingly improves, and at some point you're able to describe these strongly anharmonic rare effects. This is nice. Here we knew already what is going on. We applied that to 100 more materials where we had no idea what is going on. And what was most surprising is that some materials that are very well behaved, like silver gallium selenide here, so you see the DFT is actually well behaved. If you just blindly train your machine learning potentials, you get a strongly anharmonic effect. You get an additional minimum here that does not exist in DFT. And only if you then start this kind of active learning scheme, you see you slowly get the right, correct, more harmonic behavior. And this is something that happens quite a lot and that you might care about when training your machine learning potential. So far, so good. So what I'm trying to show you here is how we've done this heat flux, how we looked at strong anharmonicities, and I hope I could convince you that you might even care about that if you're dealing with more well-behaved materials, because exactly you don't want your system to hallucinate some strongly anharmonic effects when they're not there. And with that, I promised we go now to charge transport. So this is the second part. We slightly switch gear. That said, we have electrons, ions, and polarons playing a role here. So if you're thinking about electrons, this is typically, again, such a picture. You have Bloch states, and they get scattered by the phonons, and this is what introduces the friction in that kind of charge transport. You have ionic conduction. This is typically diffusion, so you have atoms that hold the charge hopping around. And then you have polarons that are something like a mixed bag. I'll get to that later, hopefully. First, let's just talk about phonon-hindered band transport. Again, I'm not repeat myself, you can treat it very efficiently in a many-body perturbation theory as long as anharmonicity is low. If anharmonicity gets strong, all this kind of perturbation theory breaks down. And there we need different methods. What we've done there over the last 10 years, if we tried different techniques, always starting from ab initio in D. One is basically coupling that to band structure unfolding, and this gives you some fully anharmonic renormalized electronic band structures. This is what you're seeing here. So what you see, it's no longer a sharp band structure, but you get a broadness, and this really depends on your molecular dynamics, on how the atoms move, on your temperature. And the second thing we've done, and this is basically in close analogy to what we've done in the Green-Kubo method for nuclei, here this Kubo-Greenwood formalism for electrons and phonons that essentially allows you to get mobilities or conductivities from ab initio in D at a fully anharmonic level. Let me just rapidly skim over the theory there. What you do, you start again now with a correlation function, now in its quantum mechanical formulation. You put in the independent particle flux operator, you switch to a Heisenberg picture, and then you get this kind of equation, which at the first moment looks nice. It basically describes nothing else than some transition between different states at the same K point. What you're actually describing is really optical transitions between different states. So this is for a simple system, primitive cell in equilibrium, but you don't get any low frequency conductivity. What you actually have to do to describe the system right is to describe indirect transitions. And this works by going to supercells. If you go to supercells, just going to the supercell, nothing changes. But as soon as you displace your atom, you see you break the symmetry, then this kind of transition becomes active, and you get some kind of signal here. Now, this is, I think, more in a movie. You really see how these atoms move and how basically you get more and more signal. And this is also the kind how this algorithm works. You run MD, you calculate this kind of conductivity, and then you average over it. First, this looks nice. It's a really pain to converge. You need extremely dense K-grids. You need extremely large supercells. You have to play a lot of tricks to get that right. I'm not going again into the details. Jinka, actually a PhD student that is finishing now, has really done an excellent work in really getting that right and demonstrating it for strontium titanate. And what we're showing here is that this is standard perturbative theory, or not even standard because they have renormalized phonons, but they basically overestimate the mobility by an order of magnitude. If you do some kind of cumulant expansion here in violet, you get a little bit better, but you still have the standard 1/T kind of dependence of the conductivity. And only basically if you really account for the mobility, for the nuclear motion, then you get these deviations from the 1/T law, which in close agreement here with experiment. Again, we're not just interested in reproducing numbers, we want to understand what is going on, and this is where the spectral functions start to become useful. If you look a little bit closer, in white you see the 0K band structure. In color you see actually what is the spectral function at a high temperature. You have a hard time really discovering what is going on here. If I wouldn't plot the white lines, good luck in finding the dispersion. And what this basically implies is that you get very, very broad line widths, and in turn it means minute lifetimes. That brings again to a breakdown of the quasi-particle picture. So this brings me essentially to my last point. We've looked now at this electronic transport. What about diffusion and hopping? Now, in particular, I want to talk a little bit more of this polaron stuff. If you look up your standard textbook and you think about polaron formation, what you see, what it's tells that you put in an excess charge in a dielectric, and if it's dielectric enough, you will have lattice distortion that screen this charge, and then for that you gain energy, and this stabilizes this quasi-particle, this localized charge, a polaron. Now, look here, this is for the whole polaron in magnesium oxide. We're really relaxing it down, and you see that after a while this goes down and this polaron forms. But the actual displacements here of the oxygen atoms are hardly visible. So this is the polaron charge density. or the whole polaron charge density, as a function of the relaxation. And so this is, although you have this kind of distortions, they're hardly visible. It's a very tricky thing to get that right. You have to be very accurate in all your calculation to do that. So these actual distortions are minute. This is a small polaron. There are also large polarons that I will not cover in this talk. What I was mostly want to show is that it's tricky to get this right. If you just use standard PBE, the so-called or well-known self-interaction error will destabilize this polaron. The charge does not want to localize. You can then introduce some hybrid functional, increase the amount of hybrids in there, and then you actually can stabilize this. Now, look at the range of energies. It's something like plus 2 eV minus 3 eV. Experimentalists love them. You can reproduce any experiment you want by just changing the fraction of exact exchange. For theory, it's a little bit less satisfying because you need a way to get your calculations right. Now, there's a very nice paper and work by Falletta and Pasquarello over recent years where they developed theories to use Janak's theorem to get the self-interaction, to get rid of the self-interaction and find the right amount of exact exchange for your system. I'm not really going to discuss that, but what you need to then really go on with those are large-scale hybrid functional calculations. And to do that, we have recently really optimized the hybrid functional in FHI AIM. So here you see the original implementation that was not too bad either. And now we essentially got that down to really perfect strong scaling up to 10,000 of scores. The time to solution is reduced by up to 2 orders of magnitude. You see an almost ideal order n scaling as you would expect from a localized representation of exact exchange. This implies that at some point you have a turnover where hybrids become as expensive as a normal GGA calculation when you increase the number of atoms. For typical system, it starts at something like 1,000 atoms. And then here just some example. You see here ice or saline liquid, water with 1,000 atoms, 60 seconds per iteration with exact exchange. You can go larger. This is a hybrid perovskite, a greater supercell. This is paracetamol, ice with 15,000 atoms. I think the largest that has been done is 30,000 atoms. So if you're interested in this kind of technology, it's very useful, especially for these polarons. And that brings me hopefully to in the last minutes, I can show you what we've done with all this technology. What we're interested in is not just the formation of polaron, but their dynamics, because this is what drives conduction. Now, intuitively, most people, when thinking about polarons, they think about exchange type mechanisms. This would be ionic conduction. This is not what we're talking when we're talking about polaron conduction. Polaron conduction is only the charge hopping when the atoms stay in their place. Again, here for our magnesium oxide test systems, you see the oxygen stay where it is, the lattice distortions somehow rearrange, and that brings the whole to hop from one side to another. This is a little bit problematic. Polaron dynamics is an activated process that often requires nanoseconds, when not microseconds, to describe correctly. So you want to have machine learning potentials for that, to reach the time and length scales. On the other hand, you need explicit charge transfers, so the electronic degrees of freedom. And those are not accounted for in machine learning potentials usually. So can we overcome that? Here we have basically devised a very simple strategy. You start with the energy of your full system and then you decompose it in the neutral system and then basically the excess system minus the neutral system. And then this one is easy to learn. And how can we deal with that? The interesting thing here is that if we look at those terms more closely, we see that the polar interaction are localized around the polaron. So they can again be learned with something like a machine learning potential, because that assumes that you have a local term. The only thing that you really need then is the position of the polaron. And this you can introduce here as an additional degree of freedom. You have to first evaluate it in your DFT calculation. You can do that via linearization by calculating expectation value of your polaron state. And then you can get a reliable representation via machine learned potentials. You can do that for a single polaron case. You can do the exact same gain in a type of cluster expansion model. You first do the neutral, then the individual polarons, then you do the polar-on-polar interaction. That is the usually many-body interaction expansion. And then you get nice potential that work and account for this charge. Application here is lithium titanate. For those that don't know about that material, that is a typical material used in batteries as an electrode. It has a spinel structure, but what you actually do, you have a partial lithium occupation and you have oxygen vacancies, and those leave 2 electrons behind, and then these 2 electrons form 2 titania 3+ polarons. And the interesting thing about here is that there's a lot of speculation and interest about how this polaron influence the lithium mobility. Here, in the sense of time, I'm just skimming about a little bit over it. I'm just saying, I mean, we have something like 10,000 HSE calculation to basically train this potential. And then when you do that, you get something nice out of it. Now, again, such a polaron natural elastic band method where you see how the polaron is jumping from one titania to the other. This is for the fact that we have a very simple model. This works very well, our machine learning potential. You can then even start doing molecular dynamics. You see the polaron is the blue one, it's jumping from some atoms of the other. It's not moving particularly fast, but if you run it for long enough, you can get a polaron diffusion coefficient. And this is their first interesting result that you get out of that. The polaron is several orders of magnitude faster than ions. Not too surprising, it doesn't involve any mass transport. What is more interesting is then if you start looking at lithium dynamics. So this is again a natural elastic band, but for the lithium motion. This can again be described with this machine learning potential. This does not induce that. You can then add the polaron on top of it, and then you see you do the natural elastic band on this kind of route again. You get a lowering in the barrier. And this was known because you could do that with DFT since ages, just running like that. The interesting thing is that we now can also account for the motion of the polarons. So what we do here is umbrella sampling at 300K and calculate the free energy barriers. And what you then see is that essentially the polaron adapts to the lithium motion because it's so much faster. And then you get an additional reduction in barrier that gives you enhanced lithium conductivity. And this is basically one of the first theoretical proofs that there is indeed a correlate polaron-ion dynamics happening in this kind of energy materials. Good. That brings me to the end of my talk. I'm already a little bit too long, I guess. So I just wanted to show you a little bit how we can use this combination of hybrid functionals, machine learning potentials, and a new machine learning potentials idea to describe this kind of energy and battery materials. This brings me to my acknowledgements. Here, Florian and Tom, now in Arizona, were the ones that were really doing the whole heat transport stuff over the years. Marcel doing all the machine learning heat flux, Kizung the active learning, and Marius and Jinkai really on all this electron transport. Matthias obviously overseeing that all the time and supporting that. At the same time, here the whole group, including Mariana for the exact exchange in FHI Ames. I did not talk about the eigensolvers that are equally important in that kind to reach this numerical accuracy that we need. And last but not least, we have the last work on the polarons by Matteo and Christoph and overseen by Carsten. And I mean, we've seen a lot of advertisements. So I'm coming from Berlin. If you're interested in electronic structure theory, that is really what my group is mainly doing. That is something very nice. Berlin is not too ugly as well, so this is where my office is located. When I got to know Mariana, she was also sitting, I think, over here a long time ago. We've heard a lot about bad things about Berlin weather. We find ways to cope with it. We have a vibrant nightlife with long queues up to 7 in the morning, if that's your thing. But mostly we're also quite a vibrant group, so my group is only 4 or 5 people in here. We're at least 80 now. And we're really at the end of the food chain here with electronic structure theory. That is what I'm doing. The rest of the group is really doing multi-scale modeling and basically harvesting the whole food chain of chemical engineering. So if you're interested in that, let me know. And with that, thank you much for your attention.
Thank you for the very nice talk. We have time for several questions.
Thank you, Professor, for the excellent talk. I have a question regarding the formation energies of the polarons. You use the hybrid function and as a basis exchange correlation functional, did you use PBE or?
No, I mean, for those calculation, we always use this HSE with optimized fraction of exact exchange using that work from Pasquarello that I showed where you can optimize this fraction of exact exchange to basically reduce the amount of self-interaction.
Yeah. My question is, I would expect that when you use a meta GGA, for example, R2 scan or something like that, with combined with the exact exchange, your formation energies would be a little lower because of the less self-interaction errors on the meta GGAs and the enhanced non-locality. I was wondering if you did that calculations to confirm that or.
I've never really done meta GGAs. What we did is you can do something like DFT plus U in some kind of fashion. And then if you do a systematic optimization of your plus U to basically get rid of your self-interaction, then you end up in the same kind of regime. The U has all its kind of different problems, in my opinion, but that is another talk.
Okay. Thank you very much.
Thanks, Chris, for the very nice talk. I don't have a question, I have an advertisement. The code that he talked about, the FHI AIMS, it's for academia, you can get it for free, so it's under a license, but it's based on donations, so if you're interested in that academically, it's for free. And in the tutorials that will run tomorrow and the day after, all the students can get it on an educational license anyways, and I'll tell you how to do it. It's very easy, but all of you can just try it out in your computer, whatever you want. Yeah? Cool.
Okay.
Thanks.
In the first part of your talk on the calculations of thermal conductivity, so I didn't quite follow. You treat the ions classically or quantum?
I do only classical molecular dynamics in that. I mean, as you see in the materials I've looking at are mainly inorganic. We've skimmed over the lithium there. We only used heavy inorganic materials and only 300 K and higher. So we can estimate that at least the quantum nuclear effects are much, much lower. I mean, if you would look at something like a specific heat, you're at 95% of the classical limit.
So the values for the thermal conductivity are good for large enough temperatures then, right?
Yes, in the classical limit.
Okay. And 300 K is large for the system?
300 K is good enough for, let's say, systems that are not hydrogen, not oxygen, not carbon. This is all what we don't like. So really inorganic systems, then you usually are okay with 300 K. I mean.
Okay.
Thank you for the great talk. So related to your point 5 there, so you treat the polaron like a point charge as if it's a different atom, and then you do dynamics with it.
Exactly.
And it should work with any type of machine learning potential framework, or you have a specific code? How does that work?
I think we have Maze, ACE, and NIQUIP implementation at the moment. So the paper is being written, and there will also be a package being released. One thing that I skimmed a little bit over it, just in the sake of time, it's not just a different atom. What we basically do is we use a Born-Oppenheimer approximation. So all atoms move, and then the polaron is optimized because it's an electronic degree of freedom. So we argue that it follows the rest of the nuclei adiabatically. In our opinion, it's still good enough because also the polaron state in this kind of materials is very well localized in the gap. If you get other materials and more polarons, your mileage may vary.
But then you, at each iteration, you need to calculate this and do...
Yeah, we have tried to optimize these polaron positions in each iteration, which makes it quite expensive even for a machine learning potential. So we can do something, I think, hundreds of nanoseconds, but then you really start hitting the limit of what is reasonably to do because you also need something like 10,000 atoms and 20 polarons, and it's tricky.
So just to have a sense on computational cost, this computation should be more expensive than the potential itself, or on the same scale, computationally.
I mean, do you mean on the training of the potential?
No, just the inference.
At the inference, in principle, what you can say is that you do something like 20 inferences per time step.
Okay.
For the time step, you also do be a little bit careful because you have these electronic degrees of freedom, so you cannot do really 1 femtosecond, you do half a femtosecond. So this is where, yeah, it's basically an order of magnitude or 2 orders of magnitude more expensive than your usual machine learning potential.
But that's what you need, so it's worth. Thank you.
So a very short question. So for your model for polarons, it works for both electron and holes. And can you repeat how do you, as we have time, can you repeat how you insert this polaron there? It's a particle, it's not. So just, sorry.
So good. Thank you very much. And I mean, honestly, because I was short in time, I skimmed a little bit over it. So what do? We have this system here where you see basically we have magnesium oxide and one whole polaron. So it works for electrons and holes equally. It's exactly the same formalism. So here, this is the standard DFT calculation. So you first get a training set for your neutral system. You run your magnesium oxide some way. You can even use a universal potential if you want, but that is easy to do. That is a solved problem. And then, for each kind of configuration, you run the same kind of DFT calculation, one with excess charge and one without. Okay? So the blue part, you have essentially learned already, and then you have this additional energy of the magnesium oxide with the polaron. If you subtract these two, in principle, what you have are the interaction of the polaron with the bulk magnesium oxide without the charge. This is what it's describing. This is what I essentially meant by this picture. You see, it's a localized interaction. It's not something global anymore. It's really something that is the interaction of the polaron. So what do? So for the second term, we describe that by a second machine learning potential that obviously depends on all coordinates of the magnesium oxide and the coordinate of the polaron. That is an additional particle that you introduce ad hoc, and you just need to know from your DFT calculation where this is sitting. Otherwise, it will not be describing it well. And this kind of position you get by basically a linearization of the polaron state, which tells you where this is sitting. And then you have this second potential that is described by all the magnesium oxide coordinates plus the polaron position. And then you can evaluate and learn that. And since this is a local quantity, this works nicely. And then coming back, basically, this is thing. Where do I have to then?
Machine learning potentials, the neutral ones and the charged ones. Can you run both them on?
Yes, I mean, I just add them on. I mean, this is a plus-minus game. It's like, if you think back in the old stories of formation energies for defects, you do the same thing. You do a charge calculation, you do a neutral calculation, you do a pristine calculation, you subtract them from each other, and as long as you align them to the right reference, you can combine them to extract basically a defect or polaron formation energy. And here we do the exact same, but we do it with a machine learning potential, so we really follow this old school theory of defects in semiconductors to decompose that total energy of the system into individual energies that we can then learn because they have a local representation. That is the idea.
I have seen people training potential for charge systems, but then you just run charge systems, and then you have neutral system, and then you just run neutral systems. So how do you mix them? I mean, or you just run one independently of the other?
No, basically we construct our potential by different contributions. So this is really when we done infer that. I was looking if I have the formula. No, not really. Where is it? So in principle, when we now update our potential, or you have a new step, you get new positions R1, Rn. So if we evaluate the neutral and the forces from that, and then we need to evaluate this one, But here, in each step, we need to optimize this polaron position. This is basically saying I invoke Born-Oppenheim approximation. The electronic degrees of freedom should follow my nuclei. So you optimize that part. For fixed nuclei, you optimize the electronic position, and then you evaluate it. And then you add them together, and then you should get the exact excess energy. And this is the nice thing by this kind of approach. I mean, you can do that by learning the electronic structure. You can do that by learning, I mean, there's different ideas to do that. But here we have this very naive or intuitive particle thing. And so we can add polarons, remove polarons. We can do multiple polarons at once. This gives you all the power that you have from these machine learning potentials, also for these localized charges.
Okay, any other question?
So the polaron part is a potential on 3n+1 coordinates, and you do a constrained optimization then? So you really do a constrained optimization only on the polaron position?
Yes.
Yeah.
I mean, I just need to, I mean, it's really, if you think how you would do ab initio MD, nuclei are fixed, and then you optimize your electronic structure. And this is the exact same thing. The polaron is representing your electronic degrees of freedom. Sure. You fix the nuclei, and it should move.
Sure, but I mean, just in practice, you do a constrained optimization, because the potential is still that part of the delta potential is still a function of all the coordinates.
The Python code at that point in time does not even know about nuclear coordinates.
Okay.
It's an exact
I
thing, but
understand.
so
Okay.
it's not constrained in that kind of sense.
Okay.
But yeah, we
Okay.
only optimize the electrons.
Good. Okay, yeah, okay.
Thank you very much for your talk. My question is, can you use a similar model to study excitons, I mean, another quasi-spectrals?
You're asking the hard questions, are you? So, excited states is not really my field. I mean, I've told before that there are many more people in the group, and we have one group leader that is really coming from this TDFT world, excitonic world, and so on. And I know that he's working also on excitons and this kind of ideas, but I don't know really much about what that is going. But principle on the long term, it would be desirable to do something like that.
Okay, thank you.
This session turned into a discussion, so I'll
Fine for me.
up. So what he asked about is a good idea, because you're describing a quasi-particle as a point something. But in your data set, can you calculate these polarons in different positions, or just on you fix the nuclei and see what happens with the FT? You cannot localize them in different positions, right?
No, we can localize them. I mean, there's a lot more behind it. What you can do is you can first localize it in different titania atoms, because that is the important thing, on different sites, by just changing these displacements. I mean, this is a little bit of group theory that you have go in, where these Jahn-Teller distortions come from, but if you have understood what drives this localization of different polarons on different titania, you know exactly which kind of symmetry distortion you have to apply to make it localize on a specific site. Now, lithium titanium oxide is really the simple thing. If you go to more complex battery materials, you have also different sites and species for the polaron. You can have something hopping from cobalt to magnesium in that kind. Then you can also play this game. So the kind of data set really includes that. Here you have the additional vacancy that can I also have. You can localize it closer to the vacancy, more farther away from the vacancy. So it's relatively diverse. I mean, it's we have this 10,000 HSE calculation essentially that include basically different polarons on different sites, and then also the barriers between them. So there are natural elastic band between these kind of things. So there's quite some things going on.
Okay, but in this sense, the electronic degrees of freedom are always in the minima. they
yes.
follow the
Yes, there is no non-adiabatic stuff. There is, it's always, this is why this works at all.
Yeah, thank you.
So, so once you found the mixing parameter that satisfies the self-interaction error and so on, did you check if the same mixing parameter reproduces the quasi-particle band gap of the material?
Yes, I mean, they're close by. I mean, this is not my work. This is basically Pasquarello's work, and we found it very inspiring. And what he has showed that you can, once you've optimized it for material, he tests for different kind of defect, different vacancies and different charge states, the band gap. Now, it's DFT, so you never get the complete band gap right to the last digit, but you're in the right number of ballpark. And I think it's a reasonable kind of approach to get something for materials where you maybe don't have experimental data, where you can really basically tune your alpha. And this is for many of these butter materials, you know, band gap measurements have plus minus 0.5 eV error, so it's hard to tune an alpha on that.
So the polaron dynamics is an activated process, right? So can you get the energy barrier for?
Yes, yes. I mean, this is what I mean. We trained before.
You got it from the MD simulations, the diffusion coefficient.
I mean, first we train on the DFT. So you see here that this is a natural elastic band for such a polaron motion. So you have that at the DFT. But then, I mean, with the machine learning potential, we can explore a lot more processes, not just the one that we have intuitively. So you do the polaron diffusion, then you can look what are the low barrier, what are the high barrier processes, what is really limiting. It's a little bit kind of tricky in this system because you have a lot of compositional disorders. So you really need the machine learning potential to do something like this kind of exploration of all possible barriers. So this system, for instance, is highly lithiated, so it blocks the polaron to some extent. But
okay, so we should thank you, Christian, for your work is too interesting. So
thank you.
Just one quick word. I will be processing the stuff for the visit to Sirius during lunch. So please, if you didn't fill the form, fill now. I'll also give instruction in Portuguese, sorry. Se vocês quiserem visitar o Sirius, eu vou processar isso durante o almoço. Então, se vocês ainda não preencheram o formulário, preencham agora, ok? Obrigado, pessoal. Bom almoço. Sorry? So, go to the web page, click on agenda. There's a big orange button on the top, ok? Vão à página, clique na agenda e tem um botão laranja no topo. So, also, one more announcement. We'll have the conference dinner today. So it's on the web page, the information with the address. Okay, so you can go, you go by your own. And also, each one has to pay for their dinner. Então hoje temos a conferência, jantar da conferência. Vai ser na Estância Grill. O endereço está no site. Cada um paga seu jantar. Ok? Não. Cada um vai. Ok? So you have to go by your own and pay by your own in the conference dinner, but we'll be there after the Sirius visit. Goodbye.